The observation that billions of individuals experience three spatial dimensions and one temporal dimension daily, without encountering anomalies suggestive of additional dimensions, indeed presents a robust empirical foundation for concluding that our universe operates within a 3 plus 1 dimensional framework. This actuarial perspective, drawing on the vast scale of human observations over time, implies an exceedingly low probability of undetected extra dimensions, manifesting in perceptible ways as no such disruptions have been documented in everyday phenomena. Nevertheless, theoretical physics offers frameworks that challenge this apparent simplicity. Prominent models, such as string theory and M theory, propose the existence of extra spatial dimensions, typically totaling 10 or 11 in these constructs, to reconcile quantum mechanics with general relativity and address inconsistencies in the standard model of particle physics. These additional dimensions are hypothesized to be compactified, meaning they are curled up at scales far smaller than those accessible to human perception or current instrumentation, potentially on the order of the Planck length, approximately 10 molast 35 inverse meters. This compactification explains their invisibility. Movements in these dimensions would be imperceptible, akin to how a tightrope walker perceives a thin wire as one-dimensional, despite its three-dimensional structure. Efforts to detect extra dimensions have focused on high-energy particle collisions and astronomical observations. For instance, experiments at the Large Hadron Collider, LHC, search for signatures such as the production of microscopic black holes, or the escape of gravitons into extra dimensions, which could manifest as missing energy in collision events. Additionally, analyses of gravitational waves from events like neutron star mergers have been examined for deviations that might indicate leakage into extra dimensions, though such studies have yielded no confirmatory evidence to date. Other potential indicators include explanations for the relative weakness of gravity compared to other fundamental forces, positing that gravity dilutes across extra dimensions, while other forces remain confined to our observable three. Despite these theoretical motivations, experimental verification remains elusive. Current data from particle accelerators and cosmic observations align more closely with the 3 plus 1 dimensional model, reinforcing the empirical argument. However, the absence of evidence does not equate to evidence of absence. Ongoing research at facilities like CERN continues to probe these possibilities. Thus, while the actuarial evidence from daily human experience is persuasive, the scientific community maintains an open stance toward higher dimensional models, pending further empirical substantiation.